In this lesson, we will learn how to apply normal distribution to other kinds of problems. This section presents methods for working with normal distributions that are not standard. So in those cases, the mean is not 0, or the standard deviation is not 1, or both. The key concept is that we can use a simple conversion that allows us to standardize any normal distribution so that the same methods of the previous lesson can be used. This is our conversion formula. We want to convert our data value to a z-score so that we can plot it on the standard z-axis. So the z-score formula is z equals x minus mu divided by sigma. So we're taking x, which is our data value, and we're subtracting the mean from it. And then we divide by the standard deviation. Always round z-scores to 2 decimal places because that's the way we look them up in our table. So when we have a situation where we want to convert, we have a normal distribution pictured here on the left side, and this is just showing that we have a mean, and it's any mean here, so the mean is mu. X is our data value, and we want to convert that to the standard normal distribution. So if we want to convert that to the standard, that means our mean is now 0, and then we have our x has been converted to a z-score. When we do this conversion, it does not change the position of the value. So the position of x will align perfectly with where the z-score is. So the way that we find areas when we have a non-standard normal distribution is we want to sketch a normal curve, label the mean and any specific x values, and then shade the region. So then we have to convert any x values to z-scores. So I actually like to sketch my picture after I've done the conversion, and I just sketch the one picture with the z-score. We're going to use Table A2 to find the appropriate area. Here's an example. Assume that adults have IQ scores that are normally distributed with a mean of 100 and a standard deviation of 15. So this is not a standard normal distribution. It is normally distributed. So whenever you see that phrase, you know you're working with the bell-shaped distribution curve. But the mean is not 0, it's 100, and we have a different standard deviation. So what I'm going to do is find the probability that a randomly selected adult has an IQ greater than 131.5. So what I need to do is convert that. So find the z-score first. So z is our data value, so it comes from this part of the problem here, the one that you're actually wanting to graph on the number line. You subtract the mean from it. Notice the use of parentheses here to solve that quantity. I divide by the standard deviation, 15. Okay, so when we enter this in the calculator, it's important to remember that we need to always round our z to 2 decimal places. So this answer in the calculator is exactly 2.1. So this would be 2.10. So now let's look up z equals 2.10. So we're going to go to Table A2, and we're going to look up that z value. Okay, so positive 2.10. So we have 2.1, and then we're looking at the hundredths position, which is up above at the heading of the table. So the 0 is the hundredths. So I get 0.9821. So let's go back. And what we're going to do next is draw the picture. So I have on the standard, notice that I put the mean of 0 in the middle. I didn't put the mean of 100. So you always want to graph on the standard distribution. And I approximated where 2.1 is, and I shaded to the right because I want to find the IQ greater than. Okay, so now we got our table entry, which was 0.9821. So remember that that is always cumulative area to the left of your z. So 0.9821 or 98.21% have an IQ smaller or lower than 131.5. We want to know the right side. So the total area under the curve is 1 or 100%. So we just subtract from 1 to find the other side. So I get 0.0179 or 1.79%. Okay, so now let's find an IQ score separating the top 55% from the others. Okay, so then this is a backwards problem because whenever they give us a percent, that corresponds to area. And you have to look for a direction word so that you know where you're shading. So the word top tells me that this is my extreme people to the positive side. So I'm going to try to draw a picture of that. And notice how I kind of estimated where my x would be. I know that, if I look at 0, that's going to be 50% to the right and 50% to the left. So 55% would just be a little bit further to the left. This is aligning with a negative z-score right now. Okay, so I have right now a 55% area, or 0.55 area to the right of this position. Now what I need to do is look this up in the body of my table, but I know that in the body of my table it's always cumulative area to the left. So always find the left side area. So whenever they give you a percentage and it's on the right, always get the one on the left so that you can look up the correct z. So I need to subtract 1 minus 0.55. So that equals 0.45. Okay, so I'm going to look up in the body of my table the number really close to 0.45. And I know it's on the negative side of the z-scores because I drew my picture already. So let's go ahead and look at that on the z-score. So I need to go to the negatives, and I'm going to scan through and I'm going to look for 0.45. So notice that all of these areas have 4 decimal places. So I'm looking for 0.4500, the closest that I can find to that. So it's going to be down here at the bottom. Okay, so as I'm scanning through, I see 0.4522 and 0.4483. Now I need to get the correct z, so I need to figure out which of these is going to be closest to 0.45. So I'm going to take 0.4500 and I'm going to subtract 0.4483 to figure out the distance. So that gives me That gives me 0.0017. Okay, so now let's go ahead and find the distance from 0.4500 to 0.4522. And you don't want it to be negative, so just take the highest number and subtract. So 0.4522 minus 0.4500 is going to give me 0.0022. So when I compare these, which is smaller, well, 17 is smaller than 22. So the shortest distance is going to be at the 0.4483. That's closest to 0.45. So the z that's associated with that is negative 0.1, and then I've got to go up to find my 100th position. So negative 0.13 is going to be my z. Okay, so let's go back to the PowerPoint and finish up the problem. So the closest to 0.45 is 0.4483. That's a z-score of negative 0.13. So are we done? We found the position on the number line, and it's negative 0.13, but you need to always look at the context of the problem. So this was a problem where we had an IQ score, and negative 0.13 is definitely not an IQ score, so I need to do a conversion. You could just use the z-score formula to actually do the conversion here. Okay, so remember that my z-score formula is z equals x minus mu divided by sigma. Now this time I know z, so that goes on the left side of the equation, negative 0.13. I don't know my score x, so that stays a variable. I subtract the mean and divide by standard deviation. So to solve this algebra equation for x, we're going to multiply both sides by the denominator. So I multiply 15 by negative 0.13, and over here when I multiply and divide by 15, they cancel out. So I get negative 1.95 equals x minus 100. So my last step is to add 100 to the other side to get x alone. That gives me 98.05. So my IQ score that separates the top 55% from the others is about a 98. Let's look at another example. Based on the sample results in dataset 2 of the appendix of the textbook, assume that human body temperatures are normally distributed. Okay, so when you see that phrase in a problem, you're always working with the bell-shaped curve. We have a mean, so that's mu, of 98.2 degrees Fahrenheit, and a standard deviation sigma of 0.62 degrees Fahrenheit. So the mean is not 0, so we're going to need to do the z-score conversion. Now, Bellevue Hospital in New York City uses 100 degrees or 100.6 degrees Fahrenheit as the lowest temperature considered to be a fever. So what percentage of normal and healthy persons would be considered to have a fever? So does that percentage suggest that the cutoff of 100.6 degrees is appropriate? So 100.6 degrees is my x. Okay, so that is the lowest temperature considered to be a fever. So let's go ahead and look at the setup for this problem. So a fever would be anything greater than or equal to 100.6 degrees. Alright, so let's convert that to a z-score. So notice the use of parentheses here. 100.6 is my x. I subtract the mean and divide by sigma. It gives me 3.87. So always round your z to 2 decimal places. And this is actually 3.8709. Okay, so you're looking at the third value, and if it's 5 or greater, you're going to have to round this next number up. So this is going to stay at 3.87. Okay, so next we sketch this. So sketch 3.87, and so right now this is anything greater they're diagnosing as a fever. So find the table entry for 3.87, looking that up in table A2. Now we get 0.9999. Now remember, that's cumulative area to the left. So obviously 99.99% of people are not going to have a fever when they go to this hospital. It's going to be a small percentage. So subtract that from 1. Alright, so there's a very small probability, 0.01%, of saying that a healthy person has a fever. So to continue this problem, physicians want to select a minimum temperature for requiring further medical tests. What should that temperature be if we only want 5% of healthy people to exceed it? So anytime they give a percent that's not an x, that is area under the curve. That's the shaded region. So we have to look for a direction word to know, are we shading to the right or are we shading to the left? So this is saying we only want 5% to exceed it. So that means in my normal distribution, I just want a tiny amount of people to exceed that temperature right there. So that's my sketch right there. So I have 0.05 area to the right of whatever this mark is, and so my goal is to figure out what's that z. Now anytime they give you right side area, you need to know left side area. So 100% minus 5% gives me 95%, so 0.95 area is to the left. Okay, so I know area to the left is 1 minus 0.05 or 0.95. Now when you look this up in the body of your table, notice this is not a z-score. So you're looking at 0.9500 in the body of your table. Now this is associated with a special z-score. It aligns with 1.645. Now this is not a temperature in degrees Fahrenheit, so we need to convert. So we're using the z-score conversion. Z equals x minus mu divided by sigma. I know my z, so that goes on the left. I don't know my x, my temperature. but I do know mu, so subtract that and I divide by sigma. Okay, so first step is to undo division. We want to multiply both sides by 0.62. So 0.62 times 1.645 is 1.0199. Notice I didn't round that up to the nearest tenth yet. I went ahead and left it out to about 4 places. So you don't want to round till the very end. Okay, so next I'm going to add to get x by itself. That's going to give me the value or the degrees of the temperature. So anything greater than 99.22 degrees is going to require further medical tests if they want only 5% of healthy people to exceed it.